So we're going to talk about learning to rank from clicks. We're mostly going to talk about math. Neither of us are really engineers, so hopefully this will be fun. Okay, so I'll give you a little introduction to Salesforce Search, and then we're talking about really sort of the whole pipeline here. So optimizing the relevance equation, and then A/B testing. So everything that we need to do to improve search relevance. Okay, so just a few interesting points about Salesforce Search. We're something like 100 million searches per day, so reasonable volume. And those searches are executed across different customers, obviously, so a few 100,000 different customers. And each of those customers also have different entities that they're searching across. And each of these combinations has its own distinct search index. So we really have like 1 million plus different disjoint search problems. So the main goal of this talk, we're not going to talk about the engineering that much, but just some of the math that we've used to try to improve relevance. Okay, so a few of the things that make this problem hard for us, or have made it hard. First of all, at Salesforce, trust is the #1 value. You hear that every day, multiple times a day. So what that means is all our customers' data is private. And in particular, the documents that people are searching for are private. So we can't ever look at the contents of those documents and see, does this make sense as the first search result or the third search result? We just have a document ID. So we're never going to get human-generated relevance labels. And the other thing that really makes it hard is just the fact that we have all these disjoint search indexes. So we really have over 1 million different search problems on different corpuses of documents with different population of queries, et cetera. Okay, so for this first part, I'm going to talk about how we optimize the relevance equation. So we're going to use what we have, which are search logs and clicks, to try to come up with the best relevance equation that we can. So what do I mean by relevance equation? I guess there's lots of sort of angles that you could look at this. So in this talk, we're specifically talking about where we combine the Lucene similarity with some query-independent features that we store maybe in a database. So things like page views or recency of the document, popularity, stuff like that. There was a talk earlier that talked about tuning the Lucene similarity. We're not going to get into that here. We do work on that on some different projects. But basically, this comes down to you have some, Lucene similarity. You treat it as a black box. You want to add these other boosts for popularity and recency and so forth. We've done that over the years by adding boosts both inside Solr and outside Solr in the app. And at some point, we came through and traced the path of all those boosts and figured out that our relevance equation looked something like this. So for a given query document pair, we basically combine all these scores to get a final score that we rank documents by. And so the guiding question for this project is, can we do better than that particular relevance equation? Can we combine these things in a better, more optimal way? Okay, so we have to define what better means. Again, there's lots of ways to define better. We have lots of metrics that we track, but probably the top level metric that really tells us about relevance health is this RMRR, so reciprocal mean reciprocal rank. And so, an RMRR of 1 means that everybody's clicking on the first document. An RMRR of 2 means everybody's clicking on the second document. The reciprocals just kind of take care of outliers. Okay, so the ranks that people click at, that's the main objective metric that we want to optimize. Okay, so we know what we want to make better, the RMRR. And the next question is, what tools do we have? So what data do we have to look at? I want to make this super clear. We do not have labeled data. So we can't get relevance labels. We can't get domain experts to look at the documents and say yes or no, this is relevant. We also, again, have all these slices of different data sets that are on different corpuses of documents, some of them quite small, some of them medium-sized. So we need to somehow rely on engagement as our main source of feedback. And maybe the first thing to look at there is clicks. So clicks are certainly a strong signal, but maybe not perfect. Okay, so I want to actually you to have a picture of kind of what the data looks like before we start to talk about the model. So this is processed a little bit to get in a format we like, but here's basically what we're looking at. There's a bunch of queries, and here each row is a query. And for a given query, there's a number of search results. And in this case, we're looking at queries that have 5 results. That is like our first landing page. And each of those results have 3 relevance features. So one of them, in this example, is the Lucene similarity score. One of them is a number of page views, or some scaled number of page views. And one of them is a number of inbound links. PC stands for parent-child. So for query 1, I've got a PC, PV, and Lucene score for the first record. And then I've got a PC, PV, and Lucene score for the second record up to the 5th record. And ultimately, I know what the user did with that query. So in this first row, the user clicked on the 4th result. And they might have clicked on more than one result. But this is basically what the data looks like that we have to train from. Okay, so we have these clicks. We want to know if they indicate relevance. The answer is that they kind of do, right? Like, certainly relevant documents are more likely to be clicked, but it's not the only reason a document might be clicked. It might be clicked just because it was shown first, just because there's no snippet, and so the user didn't know if it was relevant, and they had to click it to find out if it was relevant. So clicks are a signal of something, but not necessarily exactly relevance. So the strategy we decided to take is, instead of building a model for relevance, because we don't have labels for that, we just build a model for clicks, because we do have ground truth labels for clicks, tons of them, right? So what we're going to do is actually build a click model, a model that tries to predict which documents are clicked. But we're going to build it in a very special way. So if we can build it so that we kind of understand the ingredients, and it's made up of multiple ingredients. So I want a model that's based on, or that tries to predict clicks, and I want it to look something like this. Probability of a click equals F of relevance features times G of position. So this will hopefully be more clear in a second, but I want kind of a separable model that has a relevance component and also a positional bias component. All right, so that model has some assumptions that go with it, and I'll say them in plain English first. A document is more likely to be clicked if it's more relevant to the query. That's reasonable. All things being equal, documents that are ranked a little bit, or positioned higher, are more likely to be clicked. Also reasonable. And the last one is that the relevance or the probability of click of a document isn't measured on its own. What matters is both the relevance and the position of each document compared to the other documents that are shown, right? I'm more likely to click on the most relevant document and not just any relevant document. Okay, so those are the 3 assumptions we want to build into this model. And we can do that a little bit more mathematically. So mathematically, what it looks like is this. The first assumption is that the probability that a result is relevant to a user, now we're not talking about clicks, the probability that a result is relevant is a logistic function of the features. So you can see here, I've got 3 relevance features, S1, S2, and S3, and I've got 3 weights, W1, W2, and W3. And really this just says that the higher that linear sum of the W's and the S's is, the more probability that the document is relevant. If I could find those W's, that would be the ranking equation, because we want to rank the relevant documents the highest. So that's an assumption that such a thing exists. The next assumption is that the odds of being clicked are proportional to the odds that a document is relevant. But it's scaled by this positional bias factor. So all things being equal, a document at position 1, the probability of a click on that document is scaled by this positional bias factor B1 that goes with the bias at 1. And there's a different bias factor at 2, et cetera. So that's the math of the second assumption. And then when we put all these things together, we get the third assumption. So here's a nice sort of graphical view of what this model looks like. I've got one query. I've got 5 search results. Each search result has 3 features, S1, S2, and S3. They're all combined via these W1, W2, and W3. It's the same for each search result, and that's like a relevance score. But then to each, we also add a positional bias factor, B1 to B5. And at the top layer, we normalize all the probabilities, which is the same as taking what's called a soft max. And you get this really nice function at the top here for the probability of a click on a specific document at a specific position in a query. So we have a model now that tells us the probability of a click at each of those positions. We also have real data that tells us whether or not the documents were clicked. And so we use maximum likelihood to figure out what the best possible values of not only the positional biases, but also the W1, W2, and W3, which should give us a linear ranking equation. So this guy down here now becomes the new relevance equation. All right, so we can evaluate that in a couple ways. It's a click model, so we want to see how well it does at predicting clicks. So the way we evaluate it offline is we build an ROC curve. If you're familiar with those, this makes sense. Otherwise, feel free to ask me about it later. But it tells us how well we do at predicting clicks. So we have this click model that predicts clicks. We also have like a baseline model where you just say, I'm going to predict a click to be the click-through rate at position 1, or a click on document 2 to be the click-through rate at position 2. So that's like a baseline model. And if our model does better than that, it means it learned something. It has more information than that sort of baseline positional bias. So that would be how we evaluate the model offline. But of course, we're mostly interested in how well it does online. And that's when things start to get a little bit murky. So what you're seeing here is a bunch of org entity pairs. So I told you our problem is sliced up into all these different pairs. And on the x-axis is how well the model does offline. And on the y-axis is how well that model did online in an A/B test. Overall, it did great, but there's definitely some ambiguity. Some don't look so good. And this is definitely where we need to be very, very careful about statistical certainty when we're trying one model across a million different slices and there's these weird distributions. So this is actually where I then want to segue over to Tracy, who's going to talk a little bit more in detail about that A/B testing procedure.
Okay, great, thank you. Yeah, so I'll be discussing how we actually go about setting up our A/B tests and then evaluating the results to understand if the results were significant. So first, this is just kind of a high-level overview of what our A/B tests look like. So the way we do this is for each user query pair that comes in, we split them 50-50 between the A and B sets, where those with the A label see results that were ranked using the existing current algorithm, and those in the group see results that are ranked with whatever update we're proposing. Then we go ahead, and over the course of the test, we log which user queries were assigned to which label, and then the ranks of anything they clicked on. And then we go ahead and run this test and collect the data for a preset duration, usually somewhere in the range of 2 to 4 weeks. And then once we stop the test, we go ahead and analyze the results. So during my portion of the talk today, I'll be discussing 2 of these components. First, I'll focus on how, once the test is finished, how are we analyzing the results for statistical significance. And then at the end, I'll also talk about how we determine how long to run the test, which is another really important component of A/B testing. So first, how do we figure out if the tests are significant? So let's say we've run a test for 3 weeks, we've collected the results, and we're ready to analyze them. Here I have example output. So I plotted in this graph the distribution of click ranks for the A and B sets. Where on the x-axis is just ranks 1 through 25. The y-axis is frequency of the clicks, plotted on a log scale. And there were about 25,000 queries for each group. And then we observed some change in RMRR, which in this case was slightly negative. But how do we evaluate if this is actually represents some change from our updated algorithm, or it might just be sampling noise? So a lot of you have probably done hypothesis testing before. Kind of classic tool is using something like Welch's t-test, testing for the difference in means between 2 samples. And this makes a couple key assumptions. First of all, that our samples are drawn from normal distribution. And then we're also, in this case, this is specific to a test of the difference of 2 means. So if we go back here, we can see that our data is definitely not normally distributed. And in addition, we're interested in actually testing the change in RMRR and not just the average click rank. So to get around making some of these assumptions, we decided to go ahead and use simulations. And in particular, we're using something called permutation testing. And this is a tool that's been around for a while. Information you can look up on kind of the theory behind this, and I'll just go over it at a high level. So let's say we've run our test. We have experimental results labeled A and B, and here we have kind of example data where each colored block represents an observation. Now, when we set up our hypothesis test, usually the null hypothesis is that there's no difference in the underlying distribution between the A and B samples. And so if that's true, it shouldn't really matter if we shuffle the labels that these observations were assigned. So we can go ahead and actually form a permutation. So we can resample the data and form a permutation. So this is sampling without replacement. We basically use all and we just shuffle labels. So here's an example permutation where I've just shuffled one of the A labels and B labels. So we can go ahead and create a large number of these permutations. And this is the simulation portion. In a true permutation test, we could expand out all of the possible permutations of the labels. But you could see that as our sample size increased, this number would blow up, and it's not really feasible. And in practice, you can get good estimates using, as few as 1,000 to 10,000 permutations. Kind of depends on your data, what number you choose. Okay, so we have these, let's say we have 10,000 permutations or labels. For each permutation, we can actually calculate the change in RMRR for that permutation and then look at the distribution. So here I've plotted for our 10,000 permutations what the change in RMRR looks like. And we can think of this as an estimate of our null distribution. And then we can also plot in red here the actual observed experimental value. So let's say negative 1.2. And then we can use this to actually estimate what the p-value is for this test. And so the p-value is under the null hypothesis if there's really no difference between the two. This is the probability of observing a value at least as extreme as our experiment. So we can go ahead and calculate this, see that 1,600 of our 10,000 permutations had a change in RMR at least as extreme. So we get a p-value of 0.16. And so then we can conclude there was not enough evidence to reject the null hypothesis. This is an inconclusive test. So kind of a more high-level summary, we can use this p-value. If we set the significance level at 95%, we can reject the null hypothesis and say that this is a significant result. But if the p-value is too large, there's not enough evidence to reject the null hypothesis, and the test is inconclusive. So this is the general framework that we use to evaluate our results. We have a tool that we've implemented in Spark to process our logs. And so here's some example output of a series of tests we ran on 2 different orgs and 4 different entities. And they're split out by org entity pairs. And on the x-axis, I've also printed out the p-value for that test. And then on the y-axis, it's just the % improvement in RMRR, where a negative number actually represents a drop in performance. So that's something we don't want to see. And the 2 p-values highlighted in red are greater than 0.05. So those tests are inconclusive, but the other tests, we think the results are actually significant. And in particular, the 2 green bars saw a huge drop in performance. So we would maybe want to consider for entity B not rolling out those changes into production or kind of figuring out what's actually happening. Why did we see that big drop? You can see I also plotted confidence intervals here. And that's through a slightly different process than permutation testing. It's similar, but outside the scope of this talk. But we can get some confidence interval estimate also. OK. So then the next step is, before we can actually do this analysis, how do we know we're collecting enough data? And basically, how do we decide how long to run these tests? OK, so if we take a step back and think about how we set up a hypothesis test, normally we have this null hypothesis and the idea of the alternate hypothesis. And we set some critical value where we reject the null hypothesis if the p-value is less than that threshold. And usually we set this so that the significance level is 95%. So if the null hypothesis is true, our test will accurately result significant 95% of the time. On the flip side of that, using this, the alternate hypothesis is true, so maybe there's actually some difference of, let's say, 3 points in this example. We can look at the distribution under the alternate hypothesis, and using that same critical value, figure out the percentage of time we would be able to detect that the result is significant. And you can see that the 2 are linked. When you control significance level, you're also impacting the power of the test. So I won't go into any further detail, but basically, we usually set our significance level at 95%, and we want to also be able to use tests with at least 80% power. And the way you can control the power of the test is by increasing the sample size and also thinking about the size of the effect you'd like to detect. So the bigger the effect, you don't need as many samples, whereas if you want to detect a very small effect, you're going to need more samples. So if you're using a parametric approach, something like Welch's t-test, there are formulas you can use to plug in your numbers and figure out the desired sample size and how long you need to run your test. But because we're using simulations, we also need to do some more work to understand exactly how many samples we need to get a high-powered test. So the way we do this is by synthetically generating A/B tests using historical data. So first, we identify, maybe some period of time when no tests were in progress. So let's say we have like 8 weeks of data where there was no testing. And then we can use this as the pool of click data for our simulations. And again, we're doing this on an org entity basis. So then from this pool of clicks, let's say we want to simulate a test of 10,000 clicks. So we generate 5,000 clicks with resampling, and that's the A set, and then we pull another sample of 5,000 for the B set. And at this point, they've both been pulled from the same population, so any difference is just due to sampling. But what we can do is take that B set and somehow change the click ranks by a known amount. And so in the examples I'm showing you here, what we actually did is we just incremented the clicks by a Poisson random variable where the mean was equal to the effect size. So we're basically shifting the average click rank by some known amount. And then at this point, we have synthetic A and B data. We can run our permutation test, get a p-value, a 95% significance level. So at this point, we have one data point for that set of parameters, the number of clicks, as well as the effect size. So if we do this a number of times, let's say 1,000 times, we can then go ahead and calculate the power. So the percentage of A/B tests that we were actually able to detect were significant. So that's just one data point of the power for that number of clicks and effect size. So then we can do these simulations over and over, looking at a range of sample sizes, effect sizes, as well as input data. And then, and I'll show you the results of one such set of simulations. So the results I'm going to show you were generated for 15 orgs and 7 entities. And I looked at a range of click counts and effect sizes, ranging from about 500 to 200,000 clicks, and anywhere of a change in ACR of 0.07 up to 0.6. And we chose the orgs and entities so that there was a wide range in click volume as well as underlying performance, so the baseline RMRR of each org and entity. Oops. Okay, so once we run those tests, we can go ahead and pull together a curve like this. So this plot is frozen at 80% power and 95% significance level. On the x-axis, I've plotted the click count of the simulation. This is the total count over the A and B sets. And the y-axis is the simulated effect size. And then each line in this plot represents the simulations from one org entity pair. And then the color of the line represents the baseline RMRR for that particular organ entity. So you can see there's this. This is plotted on a log-log scale, and we have a nice relationship here. And this has been really helpful to our engineers to get some kind of idea. Before, it was always just a black box. They were like, oh, well, we're going to run the test for 2 weeks and see what we get. So now, for example, let's say they know they want to detect effects as small as 0.01, and that the organ entity they're interested in has a baseline RMRR of like 1.4, then they would need about 100,000 clicks. So with the insights from this type of analysis, we know how long we want to run the test. So there's just one more caveat in that we always run our tests in 7-day increments to avoid seasonality on a daily basis and also a weekly basis. So what we do is we just run the test for the first 7-day increment that we have at least that many clicks. So if we want 100,000 clicks, and let's say we hit that at 17 days, we still keep running the test until we hit the full 3 weeks and 133,000 clicks, and that's when we stop the test. Okay, so this is definitely ongoing work, and there's a lot we're continuing to explore, including tracking the sensitivity of this approach to the sampling window we use. So if we do this analysis today, and then again in 3 months, how much has that changed? It's also really important to continue to explore alternate methods of simulating the effect size. And then there's a lot of great work out there right now on supporting continuous monitoring, even when you use simulations to evaluate the significance of your test. So that's another avenue we can explore. So at this point, we're happy to open up to questions.